Welcome to today's webinar. The topic today is nonlinear reinforced concrete calculation in Rfem 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will answer your questions together with Juliane Stopper-Akdag. The presenter will be Dr. Mark Gebhardt. Both of my colleagues are responsible for the concrete development, and they are the main responsible persons for the development of the add-on geotechnical analysis. And they work also in the customer support team. You can ask questions when you click at the button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Mark. Mark, it's your turn.
Thank you, Andreas, for that kind introduction. As already mentioned, today we want to take a look at a very interesting topic, the nonlinear reinforced concrete analysis in Rfem 6. First, I would like to cover the relevant theoretical background. After that, I will present two application examples. The first is the stability analyzing using the general method. And second is the deflection check in the correct state. I will conclude the presentation with an outlook on current development in this field. The most important aspect is the nonlinear material behavior implemented for concrete. This is shown here for the uniaxial state of stress. In tension, linear elastic behavior is implemented up to the point where the tensile strength is reached. After that, a smeared damage model takes over. It accounts for fracture energy too. The stiffness of the elements is thereby reduced step by step until only a computational required minimum residual tensile strength remains. Let me take a short detour here into the smeared cracking approach. In reality, we have discrete cracks. An FE model, however, consists of elements. Our overall system is discretized into finite elements. To account for crack formation, we therefore have to adjust the material properties of an element. In practice, this means reducing the stiffness at the location of cracking. This happens with varying intensity across the elements depending on the respective cracked state. In addition, for compression, nonlinear elastic behavior is implemented up to the point where the compression strength is reached. Under loading, we followed this nonlinear curve. Upon unloading, we return to the origin. And again, upon reloading, we follow the same curve again. Once the failure surface is reached, plastic behavior follows. There, strain softening occurs. As a result, the stiffness of the material, and with it the permissible stress, decreases again down to a minimum strength. This minimum strength is required again for numerical stability. Another important aspect is accounting for the material behavior of concrete under multi-axial state of stress. Shown here, it is implemented failure surface for the biaxial state in plane stress. Under uniaxial loading, the behavior is shown here. The tensile strength in the biaxial state is denoted with FCT, and the compression strength is denoted with FC. In the biaxial tension region, so tension for an element, the strength of concrete is reduced. See here. As a result, the failure surface is reached at a lower stress. Crack formation follows. In the compression region, on the other hand, an increase in the permissible stress is required for elastic behavior, as shown here. Two models are implemented for the reduction in material stiffness. The first is isotropic damage. Here, the element's stiffness is reduced isotropically, so uniformly in all directions, independent of the loading direction. The second is anisotropic damage. Here, the reduction is applied only in the direction of the overstress, meaning the direction that generates the excess stress. Another important point is tension stiffening. This means accounting for the contribution of the reinforcement in reinforced concrete. On the stiffness side, this can also be accounted for in Rfem 6. Tension stiffening addresses the behavior in the cracked state. In the uncracked state, you see here, the reinforcement and the concrete both contribute, according to the respective stiffness. Once cracking occurs, and in the true fully developed crack state, the full load transfer would occur through the reinforcement alone. However, we have certain discretization here, as well as intermediate states. For realistic behavior, a contribution from the concrete between cracks must therefore be assumed in the initial cracking range. This contribution is what we call tension stiffening. For this purpose, we have implemented various models. The best known is probably the one according to Quast. Here, a stiffening contribution is applied depending on the stress state of the reinforcement. In practice, this is a permissible tensile stress. As the stress and the reinforcement approach the yield strength, this contribution is progressively reduced. It ultimately reaches zero at reaching the yield stress. In contrast, there is the modified Quast method. Here, the characteristic or design stress is applied first. In the cracked state, the tension stiffening then follows the system just described before. The last implemented model is the one according to Hirsu and Mo. Here, a fixed parabolic approach is applied for the post-cracking behavior of tension stiffening, up to a limit strain. We also want to take a look at the effect on our structure over time. This means the final state for which we are designing. For example, after 50 years. To do this, we need to take long-term effects into account. These effects are creep and shrinkage. Creep is the increase in strain under constant stress over time. Shrinkage is the volumetric contraction over time, caused by drying or hardening. Without restrained conditions, shrinkage leads to additional strain, meaning shortening. Under restraint, it leads to additional tensile stresses. Two methods are available for accounting for this directly. The first is the creep and shrinkage linear analysis method. Here, the static deformation is calculated once using the unmodified stress-strain curve of the concrete, shown here by the red curve. Then, for the state after, for example, 50 years, a stretched stress-strain curve is used instead. This curve is stretched by means of the creep coefficient with respect to strain. An even more precise approach is possible using the time-dependent analysis add-on, TDA. For this, the rheological model shown below is implemented, using Kelvin chain elements. To illustrate this, I have plotted here the strain of the concrete over time, with color coding for the different contributions of the elements shown on the left side. First, there is an instantaneous deformation. In this case, it's a purely elastic deformation, which stays constant over time as long as there are no load changes. In addition, the chain elements are attached through the coupling of springs and a damper. Through the coupling of a spring and a damper, each element activates after a different amount of time. These are known as so-called retardation times. The first element, for example, already becomes active after around 1 hour. It then remains active for the rest of the loading duration. The second element becomes active after around 1 day. The last element only really comes into effect after roughly 2 years, with its contribution increasing slowly. This setup makes it possible to account for nonlinear interaction within our structures. These can arise from different creep influences, from load redistribution, or in combination with our construction analysis add-on CSA. Together, they allow a realistic representation of our construction stages, superimposing the different starting times and creep curves. Now I would like to move on to the first practical example. For this, I looked around in our home region and found this motorway bridge, the so-called Muldetal Bridge. What is special here is the non-constant cross-section of the piers over their height. To illustrate the scope of the nonlinear analysis, I would like to briefly revisit the methods according to Eurocode 2. The first is the so-called nominal curvature method, which is implemented in the concrete design add-on. It is based on the equivalent member method. This means an idealized approximate buckling shape has to be selected first. The effective length is then derived from the shape. The solution itself is carried out separately, outside our system, as an analytical stability check. However, this method has certain application limitations. These limitations rule it out for our bridge pier. The first is a nearly constant stiffness, which is not given here, due to the variable cross-sections. The second is a cautiously formulated normal slenderness, which may lead to inaccuracies and for tall, slender structures. The last point, and a very important one for many cases, is the assumption for a constant normal force. This means the load can only be introduced in the actual direction at the pier head, without further consideration. As a result, things like crane loads applied along the height are ruled out. The method we want to focus on today is the general method. Here, nonlinear material behavior is assumed as the basis. Imperfections are applied to the system. The stability is then calculated with full interaction of the entire structure directly according to second-order theory. Now jump directly into Rfem 6. Therefore, we need a new model as usual. At first, we have to activate the add-ons nonlinear material behavior as well as concrete design. All other values relate to the default values. First of all, we delete all our basic objects and start with new materials. First of all is our concrete, a C50, 60, new coast base. You see, change the material type concrete. Following, we activate the anisotropic damage model. And we need now, as general diagram definition, the ultimate limit state. There, our strength parameters are reduced by partial factors. Furthermore, we don't want to use tension stiffening at this point to be on the safe side. So we have a standard characteristic behavior. Furthermore, we activate the time-dependent properties. And at this part, we only need creep. As you can see here, we have no graphical display. This is because we have no cross-section, but we will see this after. Second material is the reinforcement. That is a B550 SB. There, wonderful, it's reinforcing steel. And there we want to apply our isotropic plastic behavior. You can see here, these values are automatically applied to get our ultimate strain and ultimate tensile stress together in this nonlinear behavior. Now the cross sections are following. For easy application, we use this rectangular solid one, and there we have a width of 2 meters to a height of 5 meters for the first one. Here we can also see the advanced time-dependent properties of concrete, where you can see for creep, here the creep coefficient according to the time for this particular cross-section. Also, you can apply here additional user-defined values, but we will use today only the ones defined by the material. Another point to check is the FE mesh for the nonlinear analysis. As you can see here, it's a little coarser than this one for the linear analysis. So if you want to get a higher accuracy on your results, you just have to reduce this factor to get a finer mesh. But today, coarse mesh is enough for us. So we copy this 2 times to get our linear distribution. The second cross section is 3 meters, and the last one 8. So we're done on this point. Next one is application. We will model our beams. So, as already told, don't need design properties we use by the member set. So we have a linear contribution with centric alignment. First cross section is the first one, the second is the second one. Now at 20-meter high member, followed by a 5-meter high head for our column. Wait, this one we have to change cross sections, the contribution we want. Wonderful. So now we apply a member set here, get our imperfections and design configurations over both members. With design properties, concrete cover of XC3, 30 millimeters C norm, and a shear reinforcement with a diameter of 16 millimeter or 0.3 meters, followed by a longitudinal reinforcement with uniformly surrounding type of 86, the diameter of 20.8. So the others configurations are by default. Last point, we have to change here to get our model done with fixed support on the bottom point. So now we can start with our imperfections. Therefore, we need a new imperfection case. Well, imperfections, and there get a member set imperfection on our set 1 with according to Eurocode 2. So the height is 20.5 meters, and there are 10 columns in one row. Oh, and it's in a different and the false direction. We want it in Y directions. Great one. So this works. Now we import our global parameters. So we import them from spreadsheet. Now we have our load assumptions. To clarify some points, A is at this time the value for the length between the columns, followed by B by the width of the bridge. G is the load of the upper structure, Q by the vehicle load, and following the loads are calculated. Also, we want to apply a wind load in right direction with 1 kilonewton per square meter. So, can go on and get a new self-weight load case called G and apply a single load on top with the value of G on the upper point of the structure. Now do a new load case for the vehicle loads called Q and apply the force by components with in Y directions called H underscore Q, Z direction Q, and a moment about Y called M underscore Q. So the last load case is wind load case. Call it W. Apply as an easy assumption as a constant member set load on our member set in Y direction with a magnitude of y.55 meters. Great. So we go to our design situations. At this point, we don't need the characteristic and frequent design situations. But we need a new load combination wizard. Here we have the second order analysis, but we need the static analysis, creep and shrinkage linear. Furthermore, we have to apply a structure modification to get the reinforcement stiffness calculated within our structure. For creep and shrinkage, there's also a permanent load applicable. In this part, we use the quasi-permanent design situation load combinations. So creep and shrinkage will only be calculated for these loads, followed by, with the normal stiffness calculated, structural analysis of the loads, of the different loads from the ULS combination. So now we see our combinations are automatically generated. One further nice point is to change our static analysis settings with 4 increments to see the nonlinear calculation. You can see the change in the behavior. Afterwards, I now change to my pre-calculated model. You see now pre-calculated model with our ULS combinations. First of all, we take a look at our static structural results. Most interestingly is here the global deformation in Y direction. First, we have the creep calculated until 50 years, and then the other load is applied. We also can see this in our calculation diagrams. So this is the creeping load case of the permanent load, and this is the load case of structural load. As you can see here, there are 8 load increments. So if we make a combined option, you can also see here that the slope is slightly changing. So static analysis is with a little higher stiffness calculated. When we go back to the other ones, I can show you how you can see these results without using the creep and shrinkage linear in this with the permanent load set. Therefore, you have to consider the initial state by the creep and shrinkage and apply a normal static analysis. So creep and shrinkage is calculated here by CO7, and after this initial state, we have a normal static analysis. So we change back and see the diagram of this, and we can see this is exactly the same behavior. So the other result interesting us is the concrete design check, and this only the UL 100. So on this ultimate limit state design check, we see the interaction of the moments and the normal forces. Also for this nonlinear wonderful. Also for this nonlinear behavior. So if we open our interaction diagram, see this fatal surface here in 3 dimensions. So we have normal forces and the moments in Y and Z direction. If we now apply a moment-moment interaction, what is a slice into 3D, a horizontal one, we can also apply the actual normal force, which is minus 51 meganewton. Sorry, it's meganewton. And now you can see how this ratio here, the safety factor, is calculated. As you see here from the origin, direct linear point to this point, and when this touches the failure surface, your structure will fail. But here we only have about 73.5% ratio. So go back to our presentation and to the next example. Therefore, I will do a deformation analysis in the cracked state. We have also implemented the effective stiffness method within the concrete design add-on. There we have a inner force calculation with a linear elastic material, and afterwards there is a local reduction via the effective stiffness, and also a simplified approach to creep and shrinkage. Today we want to use the general procedure with a nonlinear material behavior and also time-dependent properties. Therefore, I have opened the old webinar model and will change this to apply a nonlinear analysis. Here we want to activate the nonlinear material behavior and change nothing else on this point. So we make a copy of our old materials to use it in the old design situations. Then change this behavior to anisotropic damage, and this again to isotropic plasticity, and use here the SLS mean values for the deformation and crack analysis. Also, we want to get realistic results using the tension stiffening approach according to Quast. Furthermore, we need to apply time-dependent properties for creep and shrinkage according to Eurocode 2. So the next thing we have to do is copy our quasi-permanent design situation and do not use it for the concrete design. We comment it with an L and also copy our load combination to apply static creep and shrinkage, linear, and also apply the member and surface reinforcement. So here we do not need the permanent load because we only want to calculate the quasi-permanent loading. Oh, I forgot something. I also have to copy this one or use this one with 10 load increments, and we save all results from the load increments. Great. Wonderful. So the old ones use the option different materials. Here we change the nonlinear material behavior by the isotropic behavior. And now we are done. So we have these 2 points and get them also the comment NL for later easier application. So now I will change again in the pre-calculated model and take a look to, at first, our deformations in the nonlinear calculation. Today we only want to take a look on this floor and therefore only activate this one. So as we can see here, the deformations are rising up with the time. Application time, the load increments. So on the last step, there is a reduced stiffness after 50 years. And now we can compare these results with the results of the linear elastic ones and can see there we have linear elastic results from static analysis without nonlinear material behavior and also without creep and shrinkage. When we now take a look to our concrete design results, we see in Cirque's limit state only for the quasi-permanent combination deformation in Z direction is a little lower. Furthermore, we can check the damage state. Therefore, you have the theta values on this design check. So go to our nonlinear calculation and see here criteria, the damage criteria. So if it's 1, it's completely damaged, and it's something between, it's partly damaged. So here we see in the first direction a damage of the columns, and the second damage we can see this. As you can see, this is quite local, where the actual nonlinear behavior is moreover all our structure. At last, we can also compare the there it is, the maximum crack width. This is also available in the nonlinear reinforced concrete results. So we go to crack width, go to the first direction and Z direction, and see here we have a crack width of only 0.046 in this direction. Oh, there's the first one there. So, and also you can get on the top side and see there's also less crack width. The last part on the model I would show you is the analysis of a real time-dependent analysis. So we activate here our time-dependent analysis and only copy our last design situation, called plus TDA, apply a new load combination wizard, change the time-dependent analysis, and have here within the static analysis now a tab called time-dependent analysis. Today we want to apply 10 time increments with a logarithmic time distribution, what fits wonderfully to the analytical creep coefficients distribution. So we see now here we have time-dependent analysis, structural modifications applied, and also static analysis. We call it ML plus TDA. And go back to our pre-calculated model. Now we will see the real time-dependent behavior. First, I would show you again the static analysis with the deformation in Z direction and also at this point. So here we have the deformation. Then you see here with after 28 days, so the first loading. All before is only to get the actual stress state for the first loading, so get a real nonlinear behavior. The last 10 steps are the time increments, increasing with logarithmic time distribution. So go there and see the deformation getting higher and higher until 50 years are reached. You see here the maximum deformation is 18.9 millimeters. Also, we can see that we have another distribution on the surface. This is caused by a different combination between the beam, the ribs, and the outer surfaces and the columns beneath these. So we have a realistic, nonlinear, time-dependent behavior. Furthermore, we can also check the crack state and see they are not completely equal and have some more localized effects. Other interesting part are the calculation diagrams. So you see here for the ML and TDA, the behavior. We have here only the nonlinear material behavior for the first 10 increments. In the future release, we also see here the time on these diagrams for easier application. This is followed by a curvature, a logarithmic time distribution, and the time-dependent behavior. Here you see the calculation for the linear creep and shrinkage calculation. This is only applied by the 10 load increments without a real time distribution. Now we go back to our presentation and to the last point, an outlook to our current development. We are currently developing a wonderful new feature what will help you to simulate realistic results, especially for the tension stiffening approach. Now we will use the so-called anisotropic augmented approach, which is completely new in the world. Therefore, we have a calculation between the angle of the reinforcement to the angle of the stresses. Furthermore, there's also a calculation of the distance between an integration point on the surfaces to the reinforcement point over the thickness. Second point is a revision of our damage results. In a future release, they were shown in tension and compression. In combination with the discrete rebar reinforcement modeling, you can afterwards very cool apply your reinforcement only where it is needed and have in this time a realistic behavior compared with a very economical design. Also very necessary point is the implementation of the nonlinear 1D results as shown for the 2D results. The last but not least point on this development is the integration of the nonlinear results into the concrete design add-on. Also on the time-dependent analysis add-on, we have further development. First of all, we will implement the relaxation of the pre-stressed steel using a so-called Maxwell chain model. And also we will implement aging for concrete. So, looking forward to see you again and hope you enjoy this little presentation.
Thank you, Mark, for your presentation. At the end of the webinar, I have additional hints for you, for example, to our online courses. There's the Rfem 6 course, that's a course for beginners, the Eurocode 2 course for the concrete design, the Eurocode 3 course for the steel design, the Eurocode 5 course for the timber design, and the Eurocode 8 course for the earthquake design. And the AI masterclass course for the use of artificial intelligence. For more information and prices, just scan the QR codes or click at the links. You can get an Rfem 6 course or an Eurocode course for free when you submit your customer project. And when we will publish it, just scan the QR code or click at the link here. And you reach a form where you can upload all your files. A hint to our free online services, for example, there's the Dlubal community. You can ask questions there, and our support team or other community members will answer you. There's the geozone tool for the determination of wind, snow, and earthquake loads. You can determine cross-section properties, download 3D models, or download the free trial versions of Rfem 6, RSTAP 9, RWind 3, or RSection. Yeah, for more information, you can visit our website, dlubal.com. You can find, for example, the recorded webinars there, knowledge base articles. You can ask the AI assistant Mia 24/7. Just try it. Okay, that should be also all from my side. I thank you for your attention. I wish you all a nice rest of the day. I hope we meet each other in a future webinar. See you then. Bye-bye.